61.
Page, what is it, page?
590.
Okay, and number what?
39.
Okay, you want to read it to us?
Yeah.
Brian, I just got your link.
You got it?
Yep. I don't know if it's working, but you just sent me a link to an iCloud file?
Yeah.
I got it. A beam of light is incident on a mirror. If the angle of incidence of this beam is increased, does the beam shift closer to the normal or farther from the normal?
All right, so some light rays angled toward what surface is it? Does it even say?
Mirror.
A mirror, okay. And the question says, as the angle of incidence increases, does it shift closer or away from the normal, right? It doesn't say about the angle of refraction. It's asking about the angle of incidence, right? Yeah, so,
I don't understand the question.
well, the angle of incidence is measured with respect to the actual normal.
Yeah.
So if I were to call this 30 degrees, and then I were to increase the angle of incidence, it means I'm making it larger, which is shifting away from the normal. So, for example, if I make the angle of incidence now 40 degrees, so the question is really asking you, do you know which way your angle of incidence is measured? It's measured from the normal.
Fraction.
I don't think he said anything about the angle of fraction,
I
right?
didn't understand that. That's what I couldn't find.
Yeah, they're not asking about the angle of fraction here. Just the angle, but with that said,
The angle of refraction would go away from that.
yeah, the angle of fraction would also increase. Both answers are increased. Because think about it. Here's your law. Guys, this is something that I think a couple of you made a mistake earlier in the year. So let's look at NR sine theta R. If we look at the value, because you guys haven't really started, did you just start triggering math? I think you're starting it today, I think, actually. You already started? Okay. So what you learn about is the sine function, and if the sine function increases from 0 to 90, the overall value increases. So if I were to take this number, and originally it were 30, and I had the sine of 30, and then I increase it to the sine of 40, for that to happen, this side has to also go up. So this angle would also increase as a result. Okay? The sine function is an increasing function from 0 to 90 degrees. Meaning, sine of 0 all the way up to sine of 90 keeps increasing the whole way through. And you can check with your calculator. Take sine of 0, enter. Sine of 10, enter. Sine of 20, enter. All the way up to sine of 90, and you'll see that the value keeps going up, further and further. Okay, so both the angle of incidence and refraction in this case would increase or move away from the normal.
And what we're talking about sine, with the formula of equal angle, it says like sine, like inverse of sine, nr over ni. Like let's say we're looking for like nr, and we have ni, and the equal angle. I don't like understand how it's like.
How would you solve for nr in this problem?
Divide and stuff.
All right, so in a problem like this, did I ask a problem like that in the problem set?
Yeah, there was one where you have to get rid of the inverse of sine, and I didn't know how to do that.
But isn't that something
Is that just some new sine?
Yeah.
That's my sine.
Yeah. Good. So think about inverse functions. When you take the function of the inverse, don't they cancel each other out? Like the sine. How do you get rid of the sine over here in the first place? You do the sine inverse, right? So to get rid of sine inverse, just take the sine on both sides. So you write the sine of theta. So it would look like this, Juliet. Sine theta c equals nr over ni. That's an I. Okay? Sine of theta c equals nr over ni. Yep, that's a good question, yeah. Dick?
You know, over 72 from page 699.
699, number 72. Good.
That's a 3-part.
Yeah.
Nice and loud, Mateo.
3-point charges lie on the x-axis.
This is a great review for the test right here, so we'll do this one together, okay? Great review for the test. And guaranteed kind of problem. Good.
Charge 1 is negative 2.1.
Tell me where it is first.
At the origin.
Okay. And it's negative 2.1?
But it's micro.
Got it.
Right, that's like the, yeah.
Yep.
Is at the origin. Charge 2 is positive 3.2 microcoulombs.
Where is it?
At the 7.5. Charge 3 is at 11 with a charge of negative 1.8 microcoulombs. What are the direction and magnitude of the total force on charge 1.
All right, so we're going to look at charge 1. That's our area of interest. I need charge 2 again, though. You said it too quick.
Charge 2 is at 7.5.
What's the charge itself?
3.2 microcoulombs.
All right. So the question is, what's going on with charge 2? That's the question we're being asked. Now, why did I put 7.5 and 3.5? He told me 7.5 and 11. But I put 7.5 and I put 3.5. Adds up to 11. So for a problem like this in your problem set, the number 11 centimeters is the object's position on the x-axis. 11 is not the distance between the particles. 11 is the position with respect to the origin. So here's the origin, 0, 0. Here's the position, 7.5. Here's the position, 11. That's what they're giving you in a problem like this. So for those that are confused about this, this is the origin. This is 7.5. This is 11, if I'm looking on the x-axis. So I wrote the numbers above to show the distance between them, yes?
On the question, I think it says what are the direction and the magnitude of forces are on charge 1.
Charge 1? 1 or 2? I thought you said 2.
What are the direction magnitude of forces are on charge 1?
Charge 1. Thank you, Juliet, because that would have been a very different problem, right? So we're looking at charge 1. Why did I move it over like that when I'm redrawing it? To emphasize the fact that both charges are going to come from the right now, and we'll see whether they're attractive or repulsive. Okay? So it looks like right off the bat I can see charge 1 is negative. If charge 1 is negative and I'm charge 1, is charge 2 going to pull me toward it or push me away? Charge 2 is going to pull me toward it. Because charge 2 is positive and I'm negative. Remember, the particle of interest is the particle you need to visualize can move. Right now, the only particle that can move is particle 1. And the question is, where would it move as a result of the other two? So because of the second particle, it would get pulled to the right. This would be a force on particle 1 as a result of particle 2. Again, the nomenclature is important here, the subscripts here. A force acting on particle 1 from particle 2. Particle 2 is pulling it that way. Jake, before I go on.
Were you in F12?
This is the force on particle 1 from particle 2. Right? F12, not F12. That's the difference there, yeah. It's going to be, in your mind, think of it as F12. The force on particle 1 from particle 2. Now, the other question, though, is this. You've got a negative charge over here. What happens with negative and negative? What do they do? Everybody. Repel. So if particle 1 is the one that could move, particle 1 could get pushed this way from particle 3. Oops. Force on particle 1 from particle 3. So that's my free body diagram. That's the most important part right here. If you can't get to this point right here, you're never going to be able to get the right answer. It's not possible to get the right answer if you don't get this part right. Because now what you're going to do is you're going to calculate the electric force between particles 1 and 2, and then the electric force between particles 1 and 3, and you're going to see which one of these is bigger. If 1, 2 is bigger, it's going to get moving to the right. If 1, 3 is bigger, it's going to get pulled to the left. So the free body diagram is the most important part. So again, here's how you do it. If you need to do this again, just in your mind, cover up the other ones and think, how would this object move? If I'm a negative particle and there's a positive one over here, that's the middle one, I would get pulled toward the positive. That's where this arrow is drawn to the right. I'm getting pulled toward particle 2, and I am particle 1. But particle 3 that's over here is negative. It's going to want to push me away because we're both negatives. We repel each other. But remember, only I can move as particle 1. So particle 1 is going to get pushed this way from particle 3. So particle 1 is going to be field force from particle 3, or particle 3 pushes particle 1 this way. Yeah.
When you're adding, just like refresher, so then it would be F12 is positive.
You always think of the numbers as positive.
Okay.
Remember, whatever the values are, you think of them as positive. And then afterward, you can say, all right, the value of this has a positive plus the negative value of this because it's the left. So you visualize when you do the formula as all positives. At the end, you think this is to the right, this is to the left, which one's bigger. Whichever one wins, that's the direction this object will field force. Okay, so let me show you mathematically what you would do real quick. What formula would I use here? What formula? Good. Now, Q1, Q2 here. 1 and 2, what are they just? What's the word for those? Yeah, but specifically, like as a substrate, what does 1 and 2 mean? Is the first object the second one? But how many objects do we have? So when we do the first one, we use 1 and 2, and the next one we use 1 and 3. So we're going to really, instead of writing FE as a subscript, if you want to, just write F12. And then at the same time, what are we going to do in a moment? We're going to calculate F13 by doing KC Q1 Q3 over R squared. Now, are the R's the same?
No.
They're not. The R12 is here and R13 is down here. So think about R. What is R? R is the distance between the particles that you're really analyzing. In this part right here, you are analyzing particles 1 and 2. So what's the distance between particles 1 and 2? Yeah, you don't have to say it. 7.5. It's right here. And then the last part says we're analyzing particles 1 and 3. So we need the distance between particles 1 and 3, which in this case would be just 11. Okay, so the second one, this is going to be 11. Now it's in centimeters, is that right? So we'll use our standard units here and go ahead and plug these in. So let's do this. I'm going to plug in. You guys can calculate on your own. I'm not going to go through the calculation process. I'm just going to show you where things would go here. So for KC, we know it's 9 times 10 to the 9. The distance R12 was 7.5 centimeters, or 0.075 meters. And the other one is 11 centimeters, which is, what is that going to give us? 0.11 squared. What are these values going to come from here? We have to consider microcoulombs for each of these. So what's the prefix we have to use for micro? Or what's the standard sign? Good, 10 to the negative 6. So for Q1 and Q2, we're going to plug in. Here, 2.1, 10 to the negative 6. Remember, I'm ignoring the negative. It really doesn't matter right now. For Q2, it's 3.2 times 10 to the negative 6. For Q13, the first one is the same, 2.1, 10 to the negative 6. The next one is going to be 1.8, 10 to the negative 6. Again, I'm not including the negative sign here because I've already taken into account attractive or repulsiveness with my free body diagram. So when we did this in class, remember, I even said to you guys, I was like, we can drop the negatives or we can keep the negatives, but at the end, remember, just to take the positive value. I think Juliet answered the question. I said we need the magnitude, right? And that's why we use the absolute value for those values. If we can quickly get these values, I can finish the problem. If you have those numbers. You have them, Ernest?
Yeah.
You have F12 and F13?
Yeah.
What do you got?
F2 is 10.752 meters. And F13 is 2.8 meters.
So everybody look at the diagram. Does that make sense what I'm drawing now? I'm taking the free body diagram and I'm replacing F12 with what Ernest said it was, which was 10.7. And I'm replacing F13 with 2.8. The arrows are indicating which way this would pull the particle itself. So obviously it would move to the right if it were able to move based on these two forces. Yeah?
It's like the part B on this question, like you said, they're not part A and part B, so like without part B, would be like which direction?
Yeah, it might say, well, for something like this, you would have to answer with the magnitude and direction. So what would be the overall net force on the particle? Which way would it cause it to move?
For the net force, you just said 2.75
Yep, that's exactly right. So that's what I was saying. Ernest asked that question before. We don't need to worry about negatives and positives here, right? Because this arrow tells me positive right here. An arrow, I should point on the video. An arrow to the right indicates that it should be positive. An arrow to the left indicates it's going to be a negative force. So we don't have to worry about our signs in a problem like this. Whatever that answer turns out to be. Okay, well, this is going to be what? Pretty much 8, 7.9. Say. Okay, any questions on this kind of a problem? We did one of these in class. Did we do it in class actually? Did you guys watch the video for this one? Yeah, it's the one that we didn't get time to. You already saw one. So you saw one example of this in class, I should say. And you should have done one of these for homework already, actually, also. So you should have done 2 of these problems, and this is the third one from your problem set. So maybe, tonight or tomorrow night, depending on if you have school, practice another one of these. How do you practice a problem like this? What do you do? Honestly. Or just what? Make it up. Make up your own numbers. These are completely arbitrary values. Literally use the same schematic, but instead of 7.5 and 11, change those locations. Change the Q values. Maybe now look for solving for particle Q2 or particle Q3 instead of Q1. We only did Q1 here. You can do this problem for Q2 and Q3, the same problem actually, for those two particles also. By the way, fun fact, if you find the net force on Q1 and then find it on Q2 and then do it again on Q3, what do you think those all are going to add up to? Yeah, it's in a state of equilibrium always, these kinds of setups. So it add up to 0.
So if you add up all the charges and
all the net forces.
the net forces in the universe, you get 0.
Sure, theoretically, but the universe is expanding, so you really can't answer yes to that.
Isn't that a theory?
Well, it's a theory that's been proven true based on the distances that signals have traveled for a long time. But yeah, I don't know. It's a great question. I would say yes because everything has an equal and opposite pair for its force. Yeah. Yes.
I had a question for 21. I'm kind of confused, like when I look at the spell, like what's the difference between Q and like Q with a 0?
All right, so Q and Q0, good question. So section 20-1 you're talking about, right? So, yes, fine. Q by itself is the source of the electric field. That's what's providing or giving off a field. That's like the Earth. It's analogous in your mind to the Earth. Q0 is called a test charge. This is something that's brought in the vicinity of the field. Like another charge that's been introduced into this field. That's like a person on the Earth. So the source pulls that charge or pushes that charge away, like the Earth would pull you toward it. Okay, so when you're looking at formulas, where do you use these? Well, this formula here, that's a good question because we should go over this formula. This is the formula for electric field from the last section. This formula involves the source, Q, and the distance from the source itself. This doesn't even involve Q0. Q0 could be involved, though, because you could use this formula, and that would be able to give you the force felt by this charge in the presence of that electric field. Again, E is the electric field itself, the intensity, the strength in newtons per coulomb. Q is this like Earth, the thing that generates a field around it. Something with a lot of charge, a sphere with a lot of charge generates a field around it. This is how far you are from that sphere. Now, if you introduce a test charge somewhere from the sphere, you could find out what the force acting on the charge would be by taking this field, whatever the answer is, and multiplying it by your test charge. Okay? Now, I'm telling you already that you could expect a mathematical problem with a 3-point system. So don't worry too much about math with this, but you should recognize that if you're given the electric field strength, you can multiply it by whatever test charge is to give you a force, or recognize that as you get further from the electric field, R increases, so the field strength goes down, or if the source strength goes up, the field strength goes up. The relationships that exist should be understood here, and doing some simple math, but this is not really a focus on the math part of the test. The other part was more of a focus. Okay? Just to give you a little preview for these are great questions, guys. This is what I really hope for every time we review. That's like 4 questions in a row already on different things that you had either trouble understanding or explaining on the problem set. It's what the problem set's for. It's really not for a grade. Don't know that. The problem set is meant for you to review to do on the test. It's not meant to make you more grades or more stuff to do really. Practice.
Did we go over you said this earlier in class that let's say one of the values is double what happens to this value? Did we go over that
for any of these?
Yeah.
In general?
Yeah.
Sure. Formula-wise, we go back as far as this for this section, where we started with V equals omega lambda. This was in 15.2.16.1 with electromagnetic radiation with like the spectrum. So it could be in this formula, it could be evolved. This one's more direct though, right? If you double this value, this would double. But because in the universe, all EM waves travel at the speed of light. Okay, if I look at this formula, it acts a little bit differently. So for this formula, this is always a constant for EM waves. So if I double the wavelength, I'd be halving the frequency. If I double the frequency right here, I would have to half the wavelength for this number to be constant. This does not change, remember, for EM waves. So this is an exception to the ideas where the other ones we're going to look at just the formulas themselves. So up here, if I look at this one, I could see that if I double Q, because these are directly related, if I double Q, I double the electric field strength. Again, think about this as being the source. If the source of the electric field doubles in strength, the field itself doubles in strength. It's like having twice as many electrons in that area. The field's going to be stronger that it produces. It's the same as the Earth's mass. If the planet's mass gets bigger and bigger and bigger, what happens to the gravity? Stronger and stronger and stronger. Like Jupiter, its gravity is much stronger because its mass is much greater than the Earth. So this is directly related, whereas the distance from the field, r, the distance from the field is indirectly related. If this were to double or triple, the field strength would go down by square of that value, because this is squared now. So if I were to triple the distance from the field, so here's my electric field, or my electric source, and I'm at some given location, and suddenly I triple the distance. I'm at some distance d, and now it's a new distance 3d. I triple the distance involved. If I triple the distance from the source, I'm tripling that r value in the denominator. So inherently, I'm doing this. I'm taking 3r, and now I'm squaring that instead, which becomes 9r squared, really. So I'd be decreasing the field strength by a factor of 9 if I triple the distance from the source. Remember, because it's the square. We've done this many times this year already. When it's a square or a square root, you have to take into account that factor with the variable. But if I were to triple the charge, it just triples the electric field. Because tripling the charge would put a 3 up here, right? That's what that would do. But that's not squared up top. Okay? So as a result, this would go up, the denominator would go up by a factor of 9, the numerator would go up by a factor of 3. So if I were to actually do that, triple the source, like put 3 times as many positive signs in here suddenly, but at the same time triple the distance, you'd end up with 3 times as much up top, but a 9 in the bottom like that. So what would that reduce to? Just 1/3. Now it depends on what formula you're looking at though. So if I look at the other formulas here, our other formula that was used, can I zoom out? Yeah, let's do that. Our other formula that we used was this one, and this is the one that we just showed a minute ago. So a problem could be asked like this, right? Both of the charges present that cause a force double in magnitude. Well, right away, replace this with 2q1, replace this with 2q2. What's 2 times 2? So you have 4 times as much force if both of the charges double, because they're multipliers, right? But if the distance changes also, then I have to consider that as well, again, for a problem like this. So let's say the distance between 2 charges, so here's the 2 charges. Let's say the distance goes up by a factor of 5. Well, this denominator now becomes 5r, that quantity squared. So if instead of the particles being this far apart, now they're 5 times as far apart, that becomes 5r. But let's say one of the particles doubles in strength, while the other triples in strength. See what I've done? I put a 2 and a 3 there now. What's 2 times 3 give me? And 5 squared, what does that give me? So what does this force change by? Well, it changes by a factor of 6/25. So if I think about that, it means I'm taking the original force it was and multiplying it by 6/25. So it would go down, really, right? It would go down. What's 6 over 25 approximately? 6 over 24 is what? A quarter. So this is approximately 0.25. You see what I'm saying mathematically? I'm saying approximately. It's approximately a quarter of the original force felt. So the original force felt between these 2 particles was some number. I don't care what it was. But the new force is around a quarter of that. Specifically, it's 6/25 of what it was. That's the kind of problem you can see when it comes to variables being doubled or tripled or quadrupled or whatever those terms are. Let's do a lot more theoretical, though. We did a lot of math just now. So theoretically, question, or you want to just...
I wanted the problem. It was 19.1 number 36 on page 698.
Page 698, number 36.
It's a question that we've given to discuss before. And it's about it was asking like, does the total charge of the universe like change?
Oh, okay. So 36 is a great question, guys. This leads us into a good discussion of theoretical stuff. The question is, does the total charge in the universe ever change?
If like something is
If something's added or whatever. The answer is no. In the universe, the answer is always no, because conservation of charge, just like conservation of energy. So that leads us to the next thing we can start talking about, which is good. If I were to charge an object by induction, by polarization, by charging by rubbing, what's happening again? There's a transfer of what? Fill in the blank. A transfer of electrons. I think you should all kind of jump on that, right? So if I'm charging this rubber object by rubbing it against the wall, and this rubber object gets a positive charge, what could you say about it? It lost electrons. Let's do that again. Again, if something gains a positive charge, it doesn't gain protons, it's just losing electrons. The wall, if this gained a positive charge, what would the wall gain? Because of conservation of charge.
So if you're doing like a question about like rubbing things together, like electrons, the only ion you should.
Exactly. So no matter what, if something gains a positive or negative charge, your answer is either electrons were added or electrons were removed. One or the other. Okay.
I can't remember if it was 19.1, but there was a question. It was like a 3-step question, a 2-step question, like A and B, and it was asking. It said the electrons in something were like 83 or something like that, and the protons were 45, and it's like, what was the charge?
Okay, that's a great question. So imagine you have some sort of an isotope where there are more electrons than there are protons, so it has some sort of polarization to it, some sort of net charge on it, right? So if something had, can I give random numbers? It doesn't matter, right? So if something had like 52 electrons and it only had 48 protons. That's the symbol for proton or electron, right? So E negative is electron, E positive is proton. If that's the case, it has how many more electrons than protons, would you say? I would say 4. So since there's 4 electrons in abundance, and it said, what's the overall charge? Well, what's the charge on an electron? What's the charge on each individual electron? We have that number somewhere. Yeah. So the abundance of charge would be 1.6 times 10 to the negative 19, but there's 4 of them, right? So what's the overall charge? It would be negative 6.4. I'm just multiplying these two numbers, times 10 to the negative 19 coulombs. Okay, good question. So whenever there's a surplus of electrons or a surplus of protons, you can simply take that surplus, or whichever one it is, and multiply it by the fundamental charge. Remember, this is called the fundamental charge. This is the charge on a proton or electron. If it's a proton, you just make this right here, positive 1.6.
And that would be given.
That's on your, this is on your formula sheet, correct? Look at the bottom of your formula sheet. It's on the very bottom. It says E equals, I don't think it says negative. I think it just says, yeah, because it can be positive or negative based on if it's a proton or an electron. Jake.
I was like, what values are we gonna have to memorize? Like,
Look at your formula sheet, see what's on there.
like are we
Okay, sorry, that's a good question because N's aren't on the formula sheet, they're given. The index of refraction, the table of N values of air and whatever, benzene, all those different things, that will be given to you on the test. Either the table's given or the N values will be given in the problem itself.
Which material has value of 1?
Only air.
Air.
Yeah. Air is an N value of 1. Everything else is greater than 1. Do we know why that is again?
Because air is the least dense.
Okay, air is like, a lot of you, by the way, use the word dense. I'd probably lean closer to the word, the word's not dense. The air isn't more dense. The material's not actually more, some of them physically are more dense, actually, yes. But the word dense isn't the right word.
isn't it a good way
Oh,
of
just
saying
less
it?
white
Because
traffic.
can't like anything be more reflective than air?
Yeah, but you could say more refractive. Not reflective. More refractive is fine. Say, benzene is more refractive than air. Water is more refractive than air. It's not really that it's more dense. It has to do with the fact that it impedes the motion of the waves more. But it's not density, actually. Okay? Just so we're clear. Because a lot of people wrote density on the lab. I don't think I really took off a lot or any, maybe a little bit. It's not really going to do with the density of the material itself.
So why does
Air impedes the least.
sorry.
The least.
Is it just because like there's less?
Well,
Also, we'd say we should electron.
air is closest to a vacuum. A vacuum is the absence of anything impeding motion at all. So when you think about materials around you, not closest in anything, but that we have, like as far as like things that would travel through them translucent.
So spaces.
There are probably other gases that you could have in a vacuum, and you put a gas in it that might have a lower end value than air, possibly. But for the ones that we refer to and stuff, I'm talking about.
Space.
Correct. No, space would be 1. Exactly 1. Air is really 1.000028 or something. Okay? So let's go back to the definition of N. N is the ratio of what over what? Anyone remember? What was the definition of N? The first thing we did.
C over D.
Yeah. And C is always the greatest number possible, isn't it? C is the greatest speed achievable, the speed of light in a vacuum. V is the speed of light in that material. In water, the speed of light is the following. That's the speed of light in water. What's 3 over 2 give you? And wasn't that, was water? No, this is glass. Glass. Water was 1.33, right? Yeah. So this was glass, I apologize. So in glass, the speed of light was 2 times 10 to the 8. So this would simplify to give us, these cancel, 1.5. This is the N value for glass. So here's the idea. N will always be greater than 1 because the denominator will always be less than the numerator. The speed of light in anything aside from air in a vacuum has to go down. So this number is always going to be less than this number. So you have a bigger number up top always. Bigger number up top, smaller number in the bottom always for the N value. So this value will always be greater than 1. Other questions? These are great questions, guys. Yeah, Ernest, go ahead.
Like the critical angle formula.
Mm-hmm.
You said NI was always a larger number and NR was always a smaller number.
Well, you need to remember for that, simply, the denominator is always going to be bigger than the numerator for that. It's kind of the opposite of what you're seeing right here. Because the critical angle formula, sine inverse, and it's always got to be going from a slow-moving material to a fast. So the NI value will always be the bigger number because it's slower to start. So since the bigger number goes in the bottom, that's what the formula is really. So you're always going to have, like, glass to air, water to air, glass to water. That's another one because glass will be 1.5, water will be 1.33. Okay, so it's always going to go from a slower moving material to a faster moving material. That causes it to bend away from the normal and it bends back in, causing total internal reflection. Remember, total internal reflection is created when the incident angle, let's jot this down because this is a common misconception. Students always calculate the refracted angle and use that. Total internal reflection is caused when the incident angle is greater than the critical angle. When the incident angle is greater than the critical angle. So if the critical angle for some material is 43 degrees, and this light ray wants to pass through the material, and it hits at an angle of 64 degrees, instead of this continuing through, that will not happen. Instead, it will get bent back, and it will be totally internally reflected. This is going from something like, let's say, glass to air. Okay, instead of transmitting through, this is going to go through, but it's going to bend back so much refraction that it refracts back into the material. And we call this total internal reflection. And that's one of the phenomena that we spoke about. We talked about lenses for a little while. We talked about lenses that causes things to converge or diverge, those two types of lenses. We talked about application of those lenses with glassware and eyewear. If you have myopia or hyperopia, right? Farsightedness, and you don't even know those words. If you have farsightedness, you should know these words, or nearsightedness. Farsightedness is when you can see far, right? But unfortunately, you can't see near because the rays focus too far, or they focus beyond the retina. So you put a converging lens in front so it converges sooner. So you should know those corrective methods. Yeah. Or an application.
You said total internal reflection occurs when the incident angle
is greater than the critical angle. Other questions? I'm trying to think of other stuff that we should review while I'm thinking. Other questions? So I already told you the kind of math problems you should know. Okay, a 3-particle system with electric force, and then something with Snell's law and critical angles and all that kind of stuff. You should know, I talked about this earlier. be able to at least give a couple examples of applications of the EM spectrum, or be able to at least pick out of a choice, right? So if I'm looking at gamma radiation, or if I'm looking at UV rays or infrared rays, like we talked about specific applications of those, and we're really focused on a couple. You should be able to at least recognize some of what those are. So maybe I would give you like 3 types of applications and ask you which type of EM wave those refer to. So if you at least know like 1 or 2 of those, you'll know them, you know? We talked about electric field lines and some rules for our field lines. I mean, if that's like a multiple choice, you should be able to know which field line rules are true, which are not true, or maybe true or false, understanding which of the 3 are correct or incorrect. We talked about the rules for electric fields, for field lines. Remember, for fields, they have to start positive and end at a negative. We always think of electric fields as what would happen to a proton. Well, a proton in the vicinity of this would get pushed away. So that's why field lines are drawn away. This was all from the last section we just did. We talked about 3 types of charging. The first one is the easiest. We've talked about it today. You charge by rubbing, contact. The second one was called induction. Induction has to do with when you bring a charged object near a neutral object. So here, take a look up. Neutral sphere, charged rod. The rod has negative charge. I bring the rod near the sphere. Since there's negative charge, all the positive particles are going to come on this side. The negatives, where are they going to go? They're going to want to go to that side. So this is going to become polar suddenly. You're going to get positives and negatives due to this negative charge. If I then hook up a wire, all of a sudden those charges, those extra charges are going to move out, and it's going to give us an overall net charge. That was induction. Polarization is when you take a charged object and bring it near the surface of another object. And it causes the surface particles to reorient themselves in what's called the dipole fashion. And that was like this. You bring something like this, a negative charged object near a wall. Well, now the wall, all the particles here are going to reorient themselves in this fashion with all positives pulled toward the surface. It's not going to lose a charge. It's a temporary charge that you're using polarization to give. That's not a positive. Okay, so all of those particles are going to realign themselves so that positive and negative contraction occurs. If you remove this, this may last for a little while, but it will naturally reorient itself after a certain, amount of time, you would say here. We talked about conductors and insulators and semiconductors and superconductors. Conductors conduct electricity. Literally, it's named by the actual name of the word. Insulators, they prevent electrical flow, like heat insulators prevent heat flow. So insulators for electricity prevent electricity to flow through it. Semiconductors are traditionally insulators that can be then made into conductors by changing something about them, the temperature, a certain atom that's added to it. And then superconductors are things that exhibit almost no resistance to electric flow within a certain temperature range. They allow for perfect electrical flow to conduct. They are the best conductors that exist. Questions? Keep thinking, guys. You got about 3 or 4 minutes still. We talked about a flashlight and the brightness of light. What do you remember from that? Remember from a flashlight, we talked about if you hold it up to the wall here and then move it outward, what would happen to the brightness? We specifically made a conclusion based on something about the shape. So if I held the flashlight up against the wall, the circle might look like this, right? But then if I move the flashlight away from the wall a certain distance, the circle increases by how much? How much does this area go up by? The square of how far you move. So the brightness goes down by the square of how far you move.
So if you move 2 feet away, it's 4 feet.
It's relative to the original spot, not feet. It's not a measure, it's a factor of increase. So if I'm here and I triple the distance, I decrease the brightness by a factor of 9. If I increase the distance by a factor of 5, so I'm 1 foot away and now I'm 5 feet away, that's a factor of increase of 5. It goes down by? What would the brightness go down by? 25.
Wait, but isn't it 1 to 5 is 4?
It's the factor of increase, not the change in length. What is 1 to 5? How do you go from 1 to 5? By multiplying by 5. That's the factor of increase. You're doing 5 minus 1, giving you 4. That's the change in distance. Again, 1 foot to 5 feet is a change in 4 feet. But the factor of increase of my distance, I go from 1 foot to 5 foot, I've changed by a factor of, remember, factors are multipliers. Factor of 5 goes up.
But there would be a question about like comparing the similarities between Ohm's law and Newton's law of gravity, the force of gravity, like the formulas.
You should know that those are related. Yeah, that's a good question. So recognizing the following, this should definitely be in the back of your mind that this is analogous to Newton's law, G m1 m2 over r squared. Yeah, you should be able to pick up on the nature of these two. Now, you should also be talking about in class that at small distances, if as to make any calculations, you should recognize that the electric force is a lot greater than the gravitational force. Remember, for small distances and small objects, the electric force is a lot stronger. That's why on the atomic level, the force of gravity is not as effective, apparent, not as meaningful, significant. Okay? I'm going to stop recording this then. I keep doing that.
You have like lose space on that?
Say again?
You have like lose space on that?
On my iPad?
Like for that app.
No, because it uses your iPad's memory, and I just once I upload a video to YouTube, I delete it.
Oh.
I don't keep all the videos. I have like 3,000 or some thousand videos. They would never hold on here.
Oh.
I delete them. It's much easier. Other questions, guys? Other stuff? Okay, make sure that you're studying. Think back to what we have. So we've got the very end of the EM spectrum, and we've got refraction, and then we've got electrical charges. Those are your 3 topics, really. Okay, keep that in mind. Name chapter 17 and chapter 19 is a big focus. Let's focus a little bit on the end. If you have a late problem set, be sure to turn it in. If you still haven't given me a project, be sure to turn it in. I need a link or a video in your drive folder of some sort. Okay, I'll try to check on those tonight to see if you're in or not.
Only one of us.
No. One per group, guys. One video per group, please. I know your groups are with, so. But it would be good to put your names in the file. You can rename it with all of your names. The group member names. I can check. Hold on.